I'd now like to welcome our first keynote for this morning, Professor Youssef Hashash. Professor Hashash holds a Bachelor of Science, a Master of Science, and a PhD in Civil Engineering from Massachusetts Institute of Technology. He began his career with PB in Dallas and San Francisco, working on several underground construction projects in the US and Canada. Youssef joined the faculty of the Department of Civil and Environmental Engineering at the University of Illinois in 1998. His research focus includes deep excavations and tunneling in urban areas, earthquake engineering, continuum and discrete element modeling, and soil structure interaction. He also works on geotechnical engineering applications of deep learning, artificial intelligence, visualization, augmented reality, image and drone technologies. He has published nearly 300 articles and is co-inventor of 4 patents. His research group developed the software program Deep Soil that is widely used for the evaluation of soil response to earthquake shaking. His work on seismic design of underground structures is extensively used in engineering practice. Youssef is the geotechnical co-leader of the National Institute of Standards and Technology, a fellow of the American Society of Civil Engineers, and a past president of the Geo Institute of the ACSE, and has also received a number of teaching, university, and professional awards, including the Presidential Early Career Award for Scientists and Engineers and the ASCE 2014 PEC Medal. He was elected to the National Academy of Engineering in 2022, one of the highest honors for a US engineer. Please welcome Youssef to the stage for his keynote presentation.
Thank you, Alison, for the introduction, and thank you, Rock Science, for the kind invitation to speak to you. I'll take you on a journey related to numerical modeling and analysis of seismic problems starting from 1D to 3D and bringing in everything, including fluid, soil, and structure interaction. My acknowledgements here, thank you, Pangea, for being a conference partner for this session, and also thank you, my PhD students. As a faculty member, I guide, I mentor, but the heavy lifting is done by our PhD students and master student. And what you're going to be seeing here is the result of about, 4 past PhDs and about 2 or 3 ongoing ones. So lots of great effort that's been done by the students. I'll start with some motivation, give you a historical perspective, considerations for seismic soil structure interaction modeling. I'll talk about developments and applications and give you some conclusions and engineering implications. So, what is motivating us? We have physical infrastructure everywhere. We are living in an increasingly urbanized world that is subject to extreme events. And the extreme event that I am interested in today is earthquake engineering. I was talking earlier to Thamer, saying, Thamer was mentioning, seems to be lots of earthquakes these days. There are earthquakes, a lot of earthquakes that happen often, and increasingly our urban areas are vulnerable for these. So we as engineers are tasked with designing infrastructure that would be able to withstand these earthquakes. And the term withstand has a lot of meaning in it and depends on the application. So why we care about it? We've seen a lot of problems. First graphic you're seeing there, looking at a significant settlement at the Kashiwazaki nuclear power plant, 2007 earthquake, 1999 Kocaeli earthquake in Turkey, and of course more recently, we have seen that earthquake in Turkey, southern Turkey and Syria, northern Syria caused a lot of damage. Failure of buried reservoirs, subway station collapse during the 1995 Kobe earthquake. We have to deal with tall buildings next to underground structures in highly seismic area. This is Los Angeles. This is damage to a concrete face rock fill dam and the damage of a joint during the 2008 Wenchuan earthquake in China. So earthquakes happen. our infrastructure experience it and damage occurs. So how have we as engineers approached this problem? For a long time, we've developed empirical methods to estimate things such as settlement, evaluate liquefaction, and develop simplified closed-form solutions to solve the problem. We also have code-based approaches. This is, for example, ASCE7 and Tall Building Initiative, and talking about how kind of the spectrum of modeling we can do from no SSI modeling, SSI stands for soil structure interaction modeling, to a full modeling of the system. And very early on, researchers and engineers recognized the importance of using computational tools to solve these problems, starting with Nathan Newmark at the University of Illinois, for example. So we found that something called the finite, elephant method is a very, very useful approach for solving this problem because it allows us to discretize the system and then solve the equations, controlling equations. One of the earliest programs related to soil structure interaction is called SoilStruct. One of the co-author of the work was Professor Wayne Clough. He's emeritus at Georgia Tech. And going back to, it was built in the 1970s and 80s, but this particular manual is 1992. And this was a program that was used to simulate excavations and excavation-induced movements. You will notice something very interesting here is the soil model that they've used is actually the Duncan-Chang hyperbolic model. It is actually the basis of models that we use extensively nowadays, which is like the Harding soil model. It goes back way, way back. And what was beautiful about this model, it recognized the importance of small strain nonlinearity in soil. And that was the key there for solving that problem. It used early finite element formulations, and it had some serious limitations. And since then, we have really gone a lot further in that space. When we are dealing with I'm kind of shifting now from static immediately to seismic. When we're dealing with seismic soil structure interaction analysis, we often start with a free field evaluation. And with that, we start with 1D site response. Some of the work we've done at Illinois that resulted in the development of deep soil is an example of that. Earlier versions would be shake, strata, and shear beam models. And it's also we do liquefaction assessment. But then we are interested in the response of infrastructure such as tunnels, tall buildings, nuclear power plants. And then we are interested in the interaction of multiple infrastructure elements. For example, a tall building with a tunnel. Why? Think base shear. Where does base shear go? We will talk a little bit about that. And then, of course, if I'm dealing with buried reservoirs, and we use those in urban areas in the United States and elsewhere in the world, or dams, we're interested in understanding the seismic behavior of the fluid as it interacts with the solid, with the structure, and as it interacts with the soil. And with these, we are going to go through a journey as I take you from 1D to 2D to 3D. And of course, I would be remiss not to mention AI and surrogate modeling. I'll touch briefly upon it, but that's the future. So if we are going to do seismic soil structure interaction, what are the ingredients? What do we need to do that? So I'm going to take you through a few key elements. And I'm going to start with something that is not numerical, which is site investigation. Site investigation is paramount, and I'll describe some key issues there. And then we are going to talk about some additional details. But in terms of site investigation, I cannot overemphasize the importance of a thorough, detailed site investigation, starting with the measurement of shear wave velocity. If you remember Dr. Poulos in his award lecture on Sunday, he talked about VS. Now, my favorite tool for measuring shear wave velocity is actually a suspension logger, or oil suspension logger. I also love CPTs as well, but CPTs have limitations in terms of the formations they can go through. if you are wanting to do any type of seismic soil structure interaction, getting a direct measure of shear wave velocity is a must. We can't, there are correlations that relate, say, SPT to shear wave velocity, but the scatter is huge. And remember why we're doing these advanced analysis, because we need to do a refinement. We have to remove, for example, conservatism from our design. It's too expensive to run these simulations. In addition to, of course, we have to do all kinds of additional other types of laboratory and field testing, but I wanted to emphasize specifically the shear wave velocity because that's where it all starts. The other thing is, which I'm also not going to spend too much time in this, but very important for seismic soil structure interaction, is the input motion. How you select it is a major issue to find motions that are representative of your design cases. You have to develop your target spectra. You have to do your matching. You have to make sure you don't distort the ground motions. You have to have the right durations. If you have a subduction zone earthquake, you are dealing with many, could be a couple of minutes of duration as opposed to, say, 50 seconds or something like that. It's a lot of work. It requires a lot of effort. In fact, I get lots of questions from users of deep soil about ground motions. And I say, well, that's actually a specialty area that requires careful consideration. You can't just pick a ground motion. And then there's the soil modeling. And I'm going to focus on one specific soil model, iSoil, which we have developed at the University of Illinois, and I'll describe it. There are other material models that are available out in the market, and each soil model has its pros and cons. If you have a highly critical facility, consider running the simulations in two different platforms as opposed to relying on a single platform. Then in terms of structural modeling, and I'm starting here talking a little bit from a geotechnical perspective, not a structural, because if I'm a structural engineer, I would be looking at, let's put some springs to represent the soil. If I'm a geotech, I'd say, let's put some pendulums, but that is really not the way to do it. If you want to do a true soil structure interaction model, you need a software platform that will allow you to equally represent with a similar fidelity both the soil and the structure. And so that becomes very important. Fortunately, we're living in an era where we can do that. And I'm seeing it not only in research, but also in engineering practice. And I'd be happy to discuss with you how we're seeing that. Now, in dealing with soil structure interaction, it turns out an interesting problem we have to often deal with is contact, the interface between the structure and the soil. And not all contacts that are implemented in finite element codes are good. They have to be dealt with carefully and with prudence. And the formulations have to be thought out very well. And whether you have a contact that allows slippage, full contact, it depends on the ground conditions, on the structure you're dealing with. But you need to pay specific attention to that interface contact because it impacts the forces that you end up experiencing. Then in terms of, as I move on to 2D and 3D modeling, representing a complex soil structure system becomes a challenge. And hence you need good meshing tools. And here I'm showing you meshes kind of developed over the years. This going back to 1998 when I was working in industry. We had to do a tunnel soil interaction. This was an immersive tunnel. And then you're seeing here the meshing tools for, say, from RS3, from LS-DYNA, and from Diana. Having a tool that allows you to build a mesh from a geometry is going to be critical. If you want to look at the future, hopefully I can simply type a prompt in my LLM and it'll develop the mesh for me. That's where we want to be in the future because it's a tremendous challenge developing these meshes. And so this is, for example, the meshing tool in RS3. Thank you, Reginald, by the way, for these. And I also went to the website as well. And so you have to be able to import the geometry. You have to be able to clean up the geometry. And you have to be able to repair the geometry, make sure you don't have distorted elements overlapping elements. It's a non-trivial exercise. And having a tool that is handy that will allow you to do that, I can tell you, I have spent lots of time when we didn't have as good tools to develop the meshes, but having these type of tools are making the development of SSI models, complex SSI models, feasible. So now let's talk about some developments and applications. So let's talk about, I gave you a feel for the ingredients. Now I'm going to give you now examples and a little bit more detail. So first thing is, in order to be able to do a seismic soil structure interaction, you need to have good representation of the seismic behavior of soil, and also, by the way, good representation of the seismic response of the structure. Now, that's outside my area of expertise. We have here our good colleague who gave a discussion about that yesterday, about all the experiments, etc. And so it's a whole area. I'm not going to claim any expertise. I'm just a consumer of that knowledge. So let's talk about modeling of soil. So what is the challenge with modeling the soil under seismic behavior? Where we are trying to do several things. So this is an idealized representation of the cyclic behavior of the soil. And I need to be able to do a representation of small strain stiffness. And what did we mention? Vs, right? And the shear modulus is rho Vs square, rho being the mass density of the soil. We need to be able to represent that. We also need to be able to represent the small strain nonlinearity. Soil behavior is highly nonlinear over a large range of strain. If you notice that figure in the middle, the vertical axis is G over G max. This is normalized by G max. And then the horizontal axis is shear strain. But notice it's on a log scale, not a linear scale, log scale, which means that the soil is highly nonlinear. We must be able to represent the soil behavior on that. And then, of course, we have the damping, which is the energy absorption. So we need to be able to represent that. We need to represent the hysteretic damping. And often what we learn in earthquake classes about macing rules. And actually, you need to have macing rules end up overestimating damping, and hence they would transmit less energy into the structure. And so we use non-macing rule. And of course, if we're dealing with sands, you need to have the volumetric change. Or if I'm dealing with liquefaction, I will have volumetric behavior that kind of gets transferred into a pore pressure generation, and I would have also liquefaction. So we developed at the University of Illinois a new material model called iSoil. We decided to implement it in Alasdaina. This is a decision we made about 15 years ago. We chose Alasdaina at the time over other software, including research-oriented software, because it was far more versatile than anything that was available to us at the time, and we can solve the problems very fast. And so we said, okay, they didn't have a good enough soil model for us, so we developed our soil model and put it in. And my former student, Dr. Ozgun Nomanoglu, he developed that, and we've published it in paper. It works very well. It has some limitations, but it turns out good enough is good enough. You do not always need to have the most advanced model. As part of my PhD work, I used advanced bounding surface plasticity models that actually are run beautifully in terms of representing clay behavior. And then later on, and a later version was done for sands. But you don't need that actually to solve many problems. So, and this model is actually pretty simple superposition of springs and sliders, but we had to, of course, translate it into 3D. It's all the details are available in our journal paper, and it allows the representation of small strain nonlinearity. Now, there is a hysteretic model within Alasdaina that can represent small strain nonlinearity. The problem is they're limited to 10 points to kind of, does it represent piecewise linear? Ours, we recommend using 30 points. It gives you a much, much better representation. So We can do that. We can now, with this model, we did extensive testing. We can represent the cyclic behavior, cyclic degradation as a result, and also we can represent volumetric change, or in this case, pore water pressure generation. The vertical axis on the graph on the right is actually pore water pressure generation as a result of cyclic shear strain. And you see we're getting to an RU near 1. RU near 1 is a pore pressure ratio, means you have liquefaction, zero or near zero effective stresses, but you would start experiencing problems in your soil even when you're short of getting to 1. And it also causes huge numerical problems, so we don't want to have zero stresses running in our numerical simulations too much. So that cyclic behavior is very important. And what's interesting is we decided to build a model that is just complex enough, but not too complex to represent the behavior, the essential behavior that we wanted to develop. Now, when you look at the model parameters, it seems like, oh my gosh, how do I develop this? Well, it turns out it's much easier. We have all what you need are standardized modulus reduction and damping curves that there are many of them published in the literature, and then 2 parameters. That's it. And that makes the material model accessible to practicing engineers. And that's the idea here and we kind of the philosophy, in fact, started with our work in deep soil and then do that. And in fact, when you use deep soil, you can export parameters for these models. So we're trying to develop advanced tools, but accessible to engineers. Because what's the use of these just sitting in a paper and no one using them? So now I'm going to show you many examples about how we are applying these and how they're working for us. And I'm going to have a combination of real case histories as well as centrifuge experiments, lab experiments as well. So the first one, which actually what really prompted us to do this was we had a research project with the with the Nuclear Regulatory Commission of the US, because they were looking at the development of all these modular reactors. If you've been hearing about those modular nuclear reactors, supposed to standardize design, make it safer in terms of, and also cut the red tape. Instead of, sometimes these nuclear power plants take 20 years to get licensed. And in fact, it just makes it just inefficient and just going through the regulatory red tape. So they wanted advanced tools to actually be able to better estimate the settlement. So we ran a series of centrifuge tests where we had a heavy structure in the middle, and it's the container of the centrifuge allow movement in 2 directions. So we can apply bidirectional motion. And then we instrumented the model. We had sand. Of course, the structure was placed on a sand. And we're interested in the settlement of dense sand. Now you may say, why? Well, you would not build a nuclear power plant on a loose sand. That would not be a good idea. But even if you build it on a dense sand, it will experience some settlements. And people are interested. Why? Because I have tubes, pipelines, utilities, connections, etc. You don't want to have too much of a movement. Otherwise, you can have damage. And damage can cause all kinds of unpleasant consequences. So we did that, and then this was where we had actually 3 PhD students. One did the lab tests, one did centrifuge tests, and one did the numerical modeling. I worked with the student who did the numerical modeling. We helped guide also the other work, a very nice collaborative effort. And then we built the simulations and ran them in Palestine. And what you're looking at here, the first 2 graphs are what we call response spectrum. This is the response of a 1 degree of freedom system to the ground motion. And you're seeing the input motion, the measured motion, and the computed motion from the analysis. You can call it predicted motions. It's, whether it's true prediction or not, that's a debatable, but it's a forward analysis. And you find that the match is pretty reasonable. We also looked at other components, Arius intensity, which is a measure of the development of energy as the shaking goes forward. And then the third 2 graphs from the top are measured settlements and the predicted settlements. And you'll see that we are doing a decent job there. And then we are looking also at pore pressure generation because it is a saturated dense sand. And so there's a partial drainage there as well. Now, you may say, well, it doesn't match the observation. I'll agree with you. But you can say that it does a good job of capturing the observation. And I agree with you on that. Because the idea of having a perfect match should always make you question the answer, because you can develop something that can exactly match one test and then does not match the rest of the test. We use the same predictive procedure for selecting material models and similar features, and then we looked at what kind of estimate it gave of the behavior. And we didn't have one motion, we had a suite of motions, including sinusoidal motions, series of also transient motions. So we looked at, collectively, we did residuals, we looked at bias in the data, and we found that our bias is near zero in the range of frequencies of interest to us. Now let me take you to another problem. Now we'll go to the real problem. You might have heard of the damage that happened at the Kashiwazaki Kariwa nuclear power plant in Japan during an actual earthquake. This is the aerial view, and there's a service hole there, and they had some settlements, 20 to 30 centimeters of settlements. And this is a cross-section of the facility, looking at some of the structures as well. And they actually had some problems during the earthquake there. And the question is, we had a free field ground subsidence at the service hall, had differential settlements at Unit 1 reactor building that caused broken pipes and flooding problem in a nuclear power plant. They had differential settlement at Unit 3, and they had a temporary shutdown for survey and maintenance. Fortunately, it wasn't as bad as Fukushima, by the way. And the objective of the study was, how do we use ice soil in Alasdaina to evaluate the seismic settlements of the nuclear power plant structure? We wanted to see how well did we do. So we built these models, fairly large models. We're talking about models of the size of anywhere between 247,000 elements to 226. So you're looking at very large models. And we had to do use our servers, 4 cores, and the simulation times were around 15 hours to 23 hours, which is, by the way, not bad. Why? Because you put it in, you come the next day, and it's done. Okay. So we did these simulations, and we then in real-world problems, you don't always have the perfect measurements, right? So you go post an event, you measure what's happening. So in this case, what you're looking at is time versus settlement. And also, by the way, we don't have even perfect estimates of ground motion, so we had to also approximate these. But you're seeing the progression of movement during the earthquake as predicted by the model. And at the end of the shaking, what you see is a bracket showing you the range of movements that were measured. And you see that, and by the way, this was a true prediction kind of work. We did not, it is still called, it's not a class A, it's a class C prediction, meaning after the event. But we did not try to tweak things to fit. That's very important. So we went through our methodology for how to obtain material model properties, etc. And we went this, and we ended up in a place which was reasonable agreement with what was measured. There was a range measured, and always show the range that was measured. And we could have also done uncertainty analysis with our simulations, but they were taking us a little bit too much time, so we didn't want to do that. Do I have till 9:45? Just want to make sure. Okay. Then we had another class of problems, and that actually was also a problem that started in the real world. And then we got a research project about it, on it at the University of Illinois. And we were interested in understanding the interaction of tall buildings and underground structures, because the question was, I have these high rises and I have a train station next to them. Do they interact? Well, so what's the issue? Tall buildings have potential to transmit forces through the concept of, if you know about base shear, when the building shakes, there's a lateral force that's being transmitted into the ground, and sometimes it goes into piles. We heard about that on Sunday as well. And so the question is, if I have a train station exactly next to the building, where does that force go? The force doesn't stop at the property boundary. Just trust me on that, okay? They don't care, these forces. They're going to go somewhere. And so therefore, what do I do with that? You'll probably see also some images from Indonesia. The student who did the work is actually from Indonesia, and he's back there working on this problem as well. So we developed a series of experiments in the centrifuge, and then we did a series of simulations numerically. Why? Because we wanted to do a little bit of ground truthing, but we don't have much data on that. And then we had to build these models that we had to look at the condition of no building, mid-rise building, and high-rise building. And we had to do a lot of effort to simplify the building because there is a limited space in the centrifuge. And so we had to idealize how many degrees of freedom. We had 3 degrees of freedom in the T mid-rise. I actually could only represent 1 degree of freedom for the tall building. Sorry, I hope you can be acceptable at least. And I'll show you how we then released that constraint because we just couldn't fit it. And we need to make sure we did not fail the buildings, because if these buildings fail while the centrifuge is spinning, you will have a problem. You'll just damage your centrifuge. So there were lots of simulations we had to do ahead of time to ensure safety, yet the viability of the results. And then we started looking at, we were focused mostly on the response of underground structure, what kind of earth pressures we were getting there. And you might have heard of something called Mononobe Okabe earth pressures. And in some places we found that we have less, and in some cases more. It all depended on the exact configuration of the tall building and the underground structure itself. Why is that relevant? Because you probably asking me, so tell me, is it this or that? No, what I'm actually trying to communicate to you is that for your own specific problem, you need to develop a model that is unique to your case to see what kind of interaction you're going to have, because it turns out to be the nature of the forces you'll transmit and the displacements are specific to the configurations of these. And here showing us a situation whereby we have very high forces, for example, in the T high-rise. Of course, as one would expect for very tall buildings, you're going to have a lot of forces. But it also depends how deep of a basement that building has. If you have shallow basement versus deep basement, because I've seen buildings in under both conditions, you will have different forces. So there's a lot of things. So in order to go beyond the centrifuge experiments, after we calibrated our models with the centrifuge experiments and with their limitations, we then ran simulations whereby we had an actual representation of the tall buildings with all their modes. We had 52-story buildings, 13-story buildings. We had more realistic representation of the foundations. We had piles, no piles, adjusted the position of our tunnels. And where our key findings were, base shear had strong correlation with the dynamics, thrust increments, and racking displacement on the tunnel. Common simplified pressure methods are not applicable in urban areas. And underground structure stiffness influences the displacement response. P ground velocity seemed to have had the most impact. We have a lot of more details on those. So we ended up, when we did all these simulations, 11,200 simulations. And those of you who know about whether you're in industry or in research, we never get our simulations right the first time. So we had to repeat this a few times. So that's why, we always give credit to our PhD students because they had to struggle through that. And then I have a lot more details on that. If you're interested, we have papers and we have a thesis to look at that. So now I'm moving to By the way, I'm still working with the same platform, solving different problems. Same soil model, same analysis platform. Other one we wanted to do work on is Port Island case in that during Kobe earthquake in Japan, where there was measurements from a vertical array, so you can see how the ground is changing the ground motion. And there, even though they did not measure polar pressures, there was clear evidence of liquefaction, because if you look at the records on the left, and as you go from the bottom to top, do you see there's a reduction in the number of these wiggles? It's filtering high frequency. Soil filters it, but then also you see some little bit long period attenuation and that amplification, and that's actually a result of liquefaction. So we did this simulation there, and we actually also got measurements that were reasonable, and we worked with Professor Izzat Idris on that. And we were able to then explore the model a bit more. Sorry, I skipped too far, whereby we looked at things like stress path, pore pressure generation to better understand that. Now, of course, I cannot verify these, but this is where you use the simulation to complement measurements, in that it allows you to explore and understand behavior in places where you don't have measurements, because we cannot measure everywhere. And also, we cannot always have instruments ready when an earthquake happens. That's another issue. That's a trick there. So another thing we did, there was a series of centrifuge tests to study liquefaction and lateral spreading. This is the centrifuge experiment. So the soil is sloped, so you can have this lateral spreading movement, and there's water. And then we did represent the fluid-soil interaction there. And then we looked at, this is looking at the ground motion time series, response spectra, pore pressure generation, excess pore pressure generation, the hysteretic behavior of the soil, and the stress paths. And we ran that for many, many different centrifuge tests. And also, we also had a few vertical arrays. That's work that's soon, hopefully, we will get it published. But again, my research approach is to not try to match one test well. My approach is to match the totality of the test by looking at residuals, at biases in our data, because that's the better way, in my view, of actually comparing the numerical predictions. So now I'll move to yet another one, and that's sort of has the namesake of the presentation, which is the fluid structure soil interaction, or you can arrange the words in any other way you want. So what is the situation? What's the issue we have here? Is that there are a number of reservoirs that were built along the west coast of the United States. They used to be open dams, and they are in urban areas. People were concerned about contamination of the groundwater, of the water that is used for municipal supply. And also these reservoirs, these dams, were actually in valuable area. And so they thought, okay, if we put the water in a reservoir, in a concrete reservoir, cover it up, I can use the top for recreation, solar panels. And we've seen all kinds of variation of those. And so what do these things look like? They look like this. I've actually been in some of those. And water reservoirs are important. Well, you want your city to have water after an earthquake event. More importantly, you need water to fight fires that happen after an earthquake. So that's critical. And what motivated this work is that actually engineers building one of these reservoirs in one of the cities somehow overlooked the seismic design. But they were doing it in 2D, all their evaluation. And I will tell you that it turns out that the response is 3D, which we didn't understand before. Hence, why we need to do 3D soil structure interaction. So these reservoirs, you have columns, tall columns that are supported by a roof slab, and the shape is like a pizza box. I hope I'm not making you hungry. Hope you had a good breakfast. So that's what we have. And clearly the joints between the columns and the floor slab and the columns and the roof slab are important. And there's something else, is that I have water there and I need to represent that water. There are many ways of representing the water. So we decided to then run a series of centrifuge experiments, first to focus on the dynamic behavior of water. Now you may ask me why. Well, turns out that many of us still use Westergaard solution and a couple of other classic solutions. By the way, Westergaard was a professor at the University of Illinois, so it was fitting that the University of Illinois made a more recent contribution in that space as well. So we did a series of experiments there, and then we did a series of experiments in the centrifuge where we also put in an idealized reservoir. But in the centrifuge we were using at the UC Davis, we don't have biaxial shaking. So what we did is we turned the reservoir at an angle, and hence it gave you a biaxial shaking. And then we did something very similar to what I just talked to you about with the tall buildings, which is after we did all of the simulation, compared it to the centrifuge, then we removed all these constraints, built our models as if we are designing a underground facility, and we did that. So we used an ALE formulation to represent the fluid, and it does a very, very good job with that. So representing the dynamics of the fluid becomes important, as opposed to just simply putting in equivalent pressures, which actually most software platforms you have to do that. And then because the box itself of the centrifuge and the reservoir, underground reservoir, there's a bit of boundary effect. So we needed to represent the actual centrifuge box as well in that. And then what we did is we did a parametric study where we removed all these constraints, these idealizations, so that we can actually look at the real behavior. We looked at the domains we needed to do was fluid, structure, and soil. We stuck with dry soil, by the way. Then we looked at the problem of fluid structure interaction, soil structure interaction, and then fluid soil structure interaction. So we brought all of these together. And then we had these models that were extensively instrumented, but then when we did the parametric study, we went for different types of soils, for soil profiles with class C, D, and E, based on ASCE 7. We looked at motions in 2D and 3D, 3D being the vertical component. And if you think about it, vertical component could be important. And we had to deal with all issues of the modeling that I described to you, building the details of the finite element model, checking, double checking, triple checking. And then we had to deal with, of course, the computational need. And then we were able to simulate things. In the centrifuge, you want to avoid failing your structures, because otherwise you'll have loose pieces and you can have a problem and damage your centrifuge. Numerical simulation, it doesn't matter. You just hit run again. So it's beautiful. So we did that, and we were able to take our models to failure, both in, we had to look at multiple conditions. One is with water and one empty. Actual centrifuge experiments, we did 3 conditions: empty, half full, and full. And you care about this because you want to make sure when the sloshing happens, because if it hits the roof, you'll have a problem. So, and then you can actually, is it working? I was going to show you, but the collapse in animation, but the bottom shows you that we actually can capture the collapse of these models. And that is really nice, that now we can see failure mechanisms, whereby our columns, say, for example, the roof there is falling, but it's actually being held by water, believe it or not. But how realistic is that's a separate issue. But then we're going to see columns that are going to fail. So we're able to do realistic things. So now I'm trying in a wrap-up mode here. We need to always, in all of these, which I didn't show you, is we always started 1D, and we started with deep soil. Then we did 1D shear beam in the Atlas Dyna platform. And then you can go, for example, 3D nonlinear, even just a 3D of the soil mass. But then I can actually have then I would put the full 3D structure. So you need to go through those steps, and you need to do it carefully. The simulations need to be carefully designed. Now, you may ask me, I wouldn't do this in engineering practice. What I'm showing you is what we do in engineering practice. This is the practice. This is what we are doing in the US. I cannot tell you so many projects where this is what we have done. And so this is not just an academic speaking to you. Okay? This is, for example, an example of simulation that was done for an actual project. This is the bottom left by my colleague, Kirk Ellison, and his team at Arab. And what they were looking at is an entire tunnel network there and the simulations associated with it. So this stuff is being used in the real world. Okay, we're doing that so that we can look at basin effects and 3D site response effects. Uncertainty means that we have to run a lot of simulations. In 1D, we have now achieved a space where we run millions of simulations, by the way. In 3D, we're in the thousands or tens of thousands of simulations. The problem is, how do you interpret data? How you deal with computational cost? Well, you need to do all kinds of things. The problem is now, if you have a lot of data, that's where machine learning becomes important. And we demonstrated how machine learning helps us very well in 1D site response to estimate site amplification. There is now things that where we now have to deal with self-learning simulations and surrogate modeling. I'm not going to go into details, but I'm just making you aware that this is now becomes feasible, and we can do it in 3D, not in just 2D. Self-learning simulation is one thing, surrogate modeling is another, but out of concern in terms of time, I shortened it. The other thing is, we have the role of large language models. And large language model, this is an example of, we may see a little bit more about it today. For example, rock science is a leader in this space, where you're using large language models, whereby you use, look what I use the word engineering speak, okay, not numerical speak, engineering speak, to build your models and run them. That's the future, so that you, the models come to you, you don't go to the model necessarily. It will allow you to create models, interpret the results of these models. This is all coming down the pipeline. It's happening where some of, as I mentioned, science is working in that space. My students were working in that space as well. So there's a lot of opportunity there. The other thing would be quantum computing. We are now hearing a lot more about it back and forth. Why it will be relevant for us? You see, everything I talk about computation time will be gone. It'll be fairly this. Now, when will that be available? I don't know. I'm not a hardware person there. But that's another place whereby... Now, why do I say this? Because when I was doing my PhD work, I was doing a 2D static excavation. It took me 24 hours. The same simulations takes me... I hit a return, sip a cup of coffee, and the simulation is done. And 3D, even 15 years ago, people say, 3D. Now 3D is pretty easy. So never say never. And specifically the young folks here. So what are my conclusions? Advances in analysis software, computing hardware, and big data management are enabling us to enter a new era of complex nonlinear seismic soil structure interaction in 3 dimensions, meaning we actually get to solve real problems. I showed you the implementation for many relevant problems, and if you're interested in iSoil, talk to me. Happy to talk to you about it. With that, I'm happy to take any questions. And
thank you very much, Professor Hashash. Please, questions from the floor? We have one over here. Thanks.
Hey, thank you, Professor, for your presentation. My question is about the iSoil model itself. You mentioned that it does not include critical state behavior, yet it has become widely accepted that critical state soil mechanics is a requirement in characterizing soil behavior. So I wanted to ask, what are some of the strengths and limitations of that model?
Sure. So we have to always think about our model relative to the application that we are interested in. While critical state soil behavior is fundamental and there's a lot of acceptance of it, but you're talking about behavior at very, very large strains. The strain ranges of the problems that I talked about actually are not very high, and hence we do not get close to critical state, except for the liquefaction problem. It turns out that even though I don't explicitly represent the critical state behavior, I get good enough answer. And that is something I want to emphasize in modeling, is that the way we have been trained is that I must have the perfect soil model to be able to implement in a perfect finite element analysis to get the perfect result. Doesn't happen this way. There are many, many soil models that, CAMCLAY model, modified CAMCLAY is a critical state model, but it cannot actually solve any of these problems. Why? It lacks small strain nonlinearity, for example. So always when we're approaching these problems, we need to have this balance. So, I was raised on critical state soil mechanics, but also the issue of where do I need it and where do I not need it? That's the question. And that's to be able to actually implement it in the field for real world problems. That is that's what we have to deal with and struggle with as well.
Thank you. Any further questions? Oh, you got hit up now, Dr. Yaqub and then Dr. Hammer.
Yeah. Thank you, Dr. Hashash. Just a general question. How do you deal with the blasting for underground? Is it a similar approach of what we are seeing, or you deal with it in a different fashion?
Sure. So I happen to have done modeling of blasting, by the way. So there are two aspects of blasting, and it depends what it is you're interested in. There's an aspect of blasting whereby you are interested in fragmenting the rock. And so you're moving from a continuum to a discontinuum. There are classes of tools that are a bit different than this to deal with that problem. Though there are within these, you can actually activate different types of elements to do that. Then there is the other aspect of the blasting whereby you're interested in the propagation of vibration and impact on infrastructure. These tools will be able to handle that for that. So it all, what it is you're trying to do, you can adjust.
Dr. Hammer?
Thank you very much, Professor Hashash, for this wonderful lecture. My question is, when you do 1 million simulations, currently, how do you summarize, or what sort of information do you glean out of it?
So actually, we did more like 6 million simulations, even though I just mentioned to you 1 million, but we actually did, because we needed to do variation in shear wave velocity, soil conditions, etc. No, we did not use Excel spreadsheets. Okay. We extensively leaned on using databases, SQLite, because we ended up with like 3 terabytes of data. And then we used Python that allowed us to automate all this data processing and then the regression of this data. So we had to do 2 types of, call it regression. One is a regression using a functional form, and we drove it with Python. And we also did and train an artificial neural network. And this data set is rich, right, with a lot of information. We also trained it, and we also use Python for that as well. So yeah, so it requires a shift in how we do that. However, let me kind of pause it. We are at the cusp of a major pivot in this space, which is using LLMs, large language models, generative AI, to drive that whole process. And hence you simply write in what I use the term engineering speak, and it'll do that for you. Now we're seeing that. We're experimenting it. I've had the privilege of with folks here as well to do that, and also done it with my students. And the promise is incredible, by the way. Hence, we'll be able to do these things. Right now, it seems insurmountable, but actually, believe it or not, it is doable. And why is that important for us? Because we saw with Pangea's acquisition of data, right? Large data sets. Because now I have to be able to bring in these large data sets, large simulations, processing, etc. We can mask all that complexity. What is interesting is that, with our phones, there's actually a massive amount of complexity that's hidden from us, by the way. We can bring a lot from lessons from that space into ours so that we allow engineers to do what they're good at, engineering.
Thank you. A final question from the floor. Clint.
Yeah, thanks very much for that presentation, Dr. Hashash. That was fascinating. I haven't seen a lot of seismic presentations. That was really fascinating. Well, first of all, the images in it gave me a new respect for the Sistine Basilica in Turkey that's been so resilient in that hotspot of seismic activity for so long. Also sort of drawing on the presentation from Dr. Harry Paulos the other day, where I noticed that a lot of piles in tall buildings are vertical. And early in my career, I'd done a lot of surveying work on jetties and bridges where there were a lot of raked piles. And I was just wondering if the use of raked piles or incorporating them into some of these tall buildings would have a positive or a negative effect when seismic activity occurs.
Sure. First, there's an issue of a little bit of a practicality. When you go for raked piles, you may end up being outside of your property line. So it's kind of a little bit difficult. I've been involved in that and sort of working with the structural engineers doing the evaluation. It turns out we don't mobilize these laterally, the piles, to too great of a depth when you're moving to develop your base shear. So I have not seen much use of raked piles for these super tall buildings. And so beyond that, I don't think I'm actually, I'd be maybe getting a little bit more into speculative territory to talk about that. But we've been able to do a lot of designs and they seem to be doing well with these. Now, of course, we saw the collapse of a building under construction in Bangkok, right? I think the jury is out on that. We still need to understand what's going on. It could be an issue with, during design, we actually do design our buildings for a level of shaking, but usually it's a lot less than what I suspect this building is. But in general, we haven't seen that to be a problem with a raked pile versus a vertical piles.
Thank you very much, Professor. Please accept this on behalf of Rock Science as a keynote speaker.
Thank you so much. Appreciate it.
Thank you again.